There's only the clean proof. And in books, they're actually, it's a pain to type. It's a pain to type a book in LaTeX, believe me. So what they'll do is they'll leave out details. So there's been kind of this thing in math that you fill in the gaps. The students are supposed to fill in the gaps. And there's a body of research in education on whether students know they're supposed to fill in the gaps. And when you quiz students and survey them, they say, well, no, the teacher's supposed to fill in the gaps. The teacher says the student's supposed to fill in the gaps. So this is typically how math classes can go in other universities, where the teacher doesn't fill in the gaps and thinks the students are going home and filling in the gaps. But that's why we don't fill in the gaps on a book. It's just, one reason is that it's impossible to, or else the book will be like gigantic. They already are. The other problem is that we actually do believe you learn a lot by filling in the gaps. That's just a sketch. But I actually, for proofwriting, I think it'd be nice to always see the scratch work and then the real proof so that people don't think it came from magic. All right, so we start out with let epsilon greater than 0 be given. And I define my letters. Let A be the soup of that sequence in the theorem. That's a new letter. What do I mean by let epsilon greater than 0 be given? What does that mean? It's on your sheet too, so. Why do I say that? Good, I was sitting in your seat back a long time ago, and I was also had no idea. Does anybody have an idea why I would say let epsilon great? These proofs all start the same.
Is it because it's your noun?
Kind of.
Is it because you need like epsilon to be greater than 0 to like you need to set?
I need a symbol. So I need the symbol to be defined, but I need it also to be arbitrary. So let epsilon greater than 0 allows it to be arbitrary. So I like to say the guy's got a bag of epsilons and they pulled an epsilon, but they haven't shown you what that epsilon is. So you have no idea, they're hiding it from you. But it's an arbitrary, it came out of a bag, it's arbitrary. A grab bag of epsilons. So let epsilon greater than 0 be given means that it's an arbitrary number. If you take EE classes, electrical engineering classes, and you look at something called the Rayleigh number, they'll use epsilons for it. They'll use it also in partial differential equations. It usually means a small number, too. Dash, question?
I was just going to ask, like, why do you have to say that, like, why do you have to let epsilon be greater than 0 to be arbitrary? Can you just leave it as it is, or?
If you don't specify it, like you're supposed to define all your variables, and now this epsilon has came in. If you go back to the theorem statement, there was no epsilon in the theorem statement. So every new letter that appears in your proof, you have to somehow define it. Now, epsilon's not an actual single value, so I have to let it be arbitrary. Okay. And so let epsilon greater than 0 be given, defines it, and lets it be arbitrary. I could say, let epsilon be an arbitrary real number, bigger than 0. I could have said that too. Okay, by definition of supremum. By the epsilon definition, the second one, I've got this. So this is the epsilon. Why am I using epsilon over 2? So the epsilon that comes from the supremum definition is not the same epsilon as the one up here. The epsilon up at the top is an arbitrary epsilon that someone's grabbed out of a bag and they haven't shown it to you yet. So that epsilon's already fixed. It's already been grabbed from the bag. But I know by the definition of supremum that all possible epsilons, it's the same, it's abusive notation. It's not the same epsilon. But you know in the definition is so I can fill in the blank. This is a definition. this is the definition of soup. I've already have the soup defined here. Let A be the soup. Well, A's got to satisfy this definition. So something can go, anything can go in the blank. So I'm going to just put epsilon over 2 in the blank. Because if you recall, the definition says for every. So that means for every epsilon that I drop the bar down a little bit, there's got to be an x value from the set inside there. So I can set it to be whatever I want, and I'm going to set it to be epsilon over 2. So again, epsilon's been grabbed from the bag. You don't know what it is yet, but you know it exists. They already have it in their hand. So you can take half of that and put it into this definition.
You could put like epsilon over 4, epsilon over 3,
Whatever you want. You could put 5 in there if you want to. It doesn't help me, but you could put 5 in there. Because the definition of supremum says for every epsilon bigger than 0, or for every blank bigger than 0. So I have my notation here. You have it on your sheet that I handed out. That's true for every epsilon, so I chose it to be epsilon over 2. So if you think of the picture, think of that limbo bar that's going down. The soup is the best bar, and then if you drop it a little bit, there's going to be members of the set that are above it. That's all that says. And just so the reader knows, I've got the sequence. There's a sequence number right here, somewhere along the middle somewhere, where this is true. So I have a picture in my mind. I actually didn't share it with you guys, but this is what's in my mind. Here's a sequence. It's leveling off. There's a supremum up here. If I drop the supremum down a little bit, this is my A. This is my A minus epsilon. This is my NK. There's got to be like if I drop that line down just a little bit, there's got to be a place where all of a sudden that definition tells me I'm going to have an element. This is A and K. We can make a couple more here. So somewhere along the line, there's going to be a sequence number that's going to be above this new, if I drop the bar down just a little bit. I guess epsilon over 2. So I've written that up here again. So I'm going to do a Dr. Calkin. I've got 2 observations. The first is that it's non-decreasing. Where's that coming from? How do I know my sequence is not decreasing? That was a hypothesis. That was inside the no. It was given. So it's non-decreasing. That's the definition of non-decreasing, that all of them are bigger or equal to. And I know that the soup is the best upper bound. That's by the first definition of the soup. Do you agree with that? Sorry, it's rusty. It's been a day since we looked at the original statement of the theorem, but you have your handout, so you can look back at the original statement of the theorem. It said, let AN be a non-decreasing sequence. Then it must converge. So that's my given. Observation number 2 is that AN minus ANK has to be less than epsilon over 2. And I'm going to show that. It's my claim. So if you're still, if you're taking notes or anything, I'm just going to the next page. So that observation 2, to see why this is true, I just pull from the this is that definition up there, and I know this is true. That's true. So far, so I'm just copying and pasting definitions. That part's by definition of the supremum being an upper bound. That part is because it's non-decreasing. So because it's non-decreasing, if I chop the sequence anywhere, there's my picture in my head. If I chop the sequence anywhere right here, all of the other ones got to be bigger.
What is A and K again?
It's that place if I lower that limbo bar, comes from this definition, there's gotta be a sequence member that's above it, by definition of soup.
Those are A and K.
That's, I just called it A and K, just to label it somewhere. So it's a fixed element in the sequence, so that when I lowered that soup down, it was the first element that was bigger than it. Make sense? So that's the epsilon definition of the supremum. That's where that one comes from. In these proofs, you're always supposed to find the n. Given epsilon greater than 0, there exists an n. So if you're proving something, you have to say, here it is, here's the capital N. I've got my capital N. See, look, that's the picture right there. If I drop down, all the other sequence members are going to be above it. So that's going to be my capital N. So that's true now for all little n's bigger than or equal to n. Now, what I'm doing is I'm piecing together the definition of a limit. I'm making it look like the definition of a limit. So I'm just now doing all the math, the algebra I did the other day. Now I'm going to subtract through by a sub n from that inequality. I'm just going to subtract a sub n from here, a sub n from here, a sub n from here. Seventh grade algebra. For some people, it's high school algebra. So it's just easy math. And then this is the soup. It's the upper bound. If I subtract that, it's bigger or equal to 0. I can take these two guys and replace it with a 0 below. So I get that. All I'm doing right now is 7th grade math. Instead of with x's, I'm just doing it with sequence numbers. Remember that thing? If you multiply by a minus sign, the inequality all turns around. That's positive, so the absolute value is the same thing. So I've got that. Right? So now I'm going to triangle inequality this thing. I'm now going to make it look like the last part of the sequence definition, sequence converging. For all n's bigger or equal to capital N, which is my nk, just reminding the reader, I've got this, which is the same as this, add a 0, and then split it up. Should be less than or equals, not equals. Less than or equals here. There's your correction by triangle inequality. Copy paste is awesome. Oops, not that. There it is. I know this is less than epsilon over 2 because of the definition of the soup. This was observation number 2, which I did the 7th grade math for. And so I get that this guy, for all little n's bigger than or equal to capital N, is smaller than epsilon, which is the definition of the sequence, convergent. And just a conclusion, we've shown that given that epsilon greater than 0, there is an n such that an minus a is less than epsilon for all n bigger or equal to n, and therefore, by definition of convergence, this limit converges to the soup.